Good morning. Let's see.
Good morning.
Happy Tuesday. It is Tuesday. Let's see. I'm just going to pull up a couple questions. From 8.6. Let a few stragglers roll in. So, I sent you an email yesterday telling you that we were not, is this the right section? 7. Telling you that we were not going to cover the 8.7 section in the interest of time, but I do at least want to show you something about it. So let's do that really quick. Let me pull up a question from 8.7 homework. Let's see here. Because I would like you to actually understand this section, even though I don't think it's worth an assignment. Write a second one down. Okay, cool. Let's try these. So, what you've realized, and many of you, excuse me, mentioned in the last section was that, man, right here at the end, we get into the weeds. I mean, these are ugly, and that's kind of true. That's where you are. You're at the limit of what integral taking involves. Like it just gets sort of weirder and crazier, and it gets much crazier than this in the sense that, if we attempt to find integrals of certain statements, like, man, we could be here for a month, and it might be impossible. And so the good thing is we're sort of done with the difficulty of that. The things I would like you to understand, if I'm careful on a test, and I gave you a review for this as we kind of get ready for a test next week, but is if you recognize the Pythagorean theorem in this statement and basic substitution, you have two basic rules: substitution and integration by parts. And if those aren't working right, then you have kind of two other options. Trig substitution. Hey, look, the bottom of that has the square root of x squared minus 16. That looks like Pythagorean theorem. And so you can make a trig substitution there, letting x be some trig statement, which seems really crazy. And then you actually can get out of that mess. And so that's kind of cool. So, and that comes up not infrequently. I showed you that kayak buoyancy thing yesterday, and that came up for me. The ability to do a trig substitution there allowed me to get that integral right. So that's worth knowing. That's kind of cool. And then we waded a little bit into just trig equations at all. Like, what's the integral of tangent cubed? And that's what we're going to talk about in a second here. What's the integral of tangent cubed? And oh man, we got to make some substitutions and make some changes. And so we waded a little bit into that. but we saw that in a sense, I'd like you to understand, it's like the water just gets deep and, goes off, and we could make this class a 2-year class going crazy looking at integrals. And so fortunately, that's kind of where the difficulty of integrals ends ultimately. And so what we're skipping in 8.7 is to take hard questions like this and say, okay, we've built a table, and we did some of them. We made some of the parts of that table that were confusing. We actually made that first one, except it was just e to the x times sine of x. And we saw, if you happen to remember, that we did integration by parts twice, and we actually found an answer to it. And that was very surprising and complicated, and the kind of thing you would never think about with as little practices we're giving. But we made an integral for that. We made the answer for that. And so the idea is at some point you kind of have this table of integrals that you've taken. I've already shown that to you. And now you just refer to that. Like you only make it once, and from then on you refer to it. And so 8.7 is saying, well, let's just start using the table then. Let's use the table to find the answer to some of these. And so let's take a look at that. Let's just take a look at that concept right now. So let's see, e to the x sine of x. And so, except for it's actually 4x. So let's go take a look at the trig table. Did I already bring this in here? The integral table, sorry. See if we can find it. Yeah, there it is. Would you agree that number 95 is what we're looking for, except for it doesn't say e to the 4x sine of 4x. It says e to the x sine of x. And so can we recognize that it's close to that and then make a substitution? And then we're given the answer here. Again, we made this exact one time. Or wait a second, look down below, 96. 96 already has that complete for us. In other words, for 96, like b is 4 and a is 4. And so, we could even use that one and it'd already be done. But let's just make this one for ourselves using 95. Let me see if I can. I think I should be able to snap a picture of this, shouldn't I? And just bring it over there. Yeah, baby. So number 95. Beautiful. So it looks like that one. And so if we say, okay, let's not build this from scratch. Let's say it's okay. And some of you asked yesterday, either right at the end or after class, can we use the trig table for this next test? Because there's some of these questions that are terrifying. And the answer to that is kind of yes. I mean, I will ask you to build some of them yourself. You can't just use the trig table for every one of them. But when they get hard, this is an example question. This example is a question that we don't. I mean, it would take an hour to do this by hand, and so let's use this. And so let's see if we can get this to look the same. Well, based on substitution, if I let u be equal to 4x, because remember, I'm trying to get it to look like this. So I say, awesome. Then if that's the case, I would have the integral of e to the u. Check, looks like that integral over there. And I'd have sine of u. Awesome. And now I just need du. But as you know, I can't just stick du there. I have to go on and say the derivative of u is the derivative of u. The derivative of 4x is the derivative of 4 times dx. And so dx is actually du over 4. And you say that's no problem because I can just pull that 1/4 out front. So I just have e to the u, sine of u, du. Chang, looks exactly like that. I'm done. All I have to do is just say, good, there's what it expands to. So let's see, I guess that'd be 1/4 times, they're telling me the integral is 1/2 times e to the whatever your x value is. For us, that's u, times the parentheses sine of u minus cosine of u. Bam, I'm done. Except for, remember, we got to put the x back in it. We got to resubstitute. There was never a u in this problem, so we got to resubstitute it. So I also noticed that 1/4 times 1/2 is 1/8, so I can throw that in there. So 1/8, and then everything else is just e to the 4x. U is replaced with 4x times sine of 4x times minus cosine of 4x. And it is nice to put brackets and parentheses when there's two sets so nobody gets confused. And again, technically there'd be kind of a plus c on the end of this. And so there, I found the integral of a ridiculously complicated statement, but I just used the integral table. And there's many integrals on that table that you can appreciate. Probably spent someone forever. They probably spent hours trying to come up with these things. And so for you practical people, I mean, most of you are taking this class because somebody wants you to take it. If you're a math major, then you want to have a better theoretical understanding. But if you're like me, somebody likes engineering, you're not going to take integrals by actually trying to make substitutions and so forth. I've showed you how to cheat in Desmos. That's what you're going to do. As soon as you can write the integral, you're done. As long as you can write it down. And there's never any non-definite integrals. Notice this one is not evaluated from, 4 to -2 or something. So you're never going to do that in the real world. There's always going to be numbers. You're trying to find the area under a specific curve between a couple of values. And so if I had those values, I could have just typed that into Desmos and I would have known the answer. I don't have to take any integrals. Easy. So in a sense, from now on, we're sort of talking about the practical side of taking integrals. Like we're not going any further into that deep water. We're going to punt now and take advantage of an integral table to answer our questions. Do you see logic in that? Now, I'm not going to put a test question on like this just because I'm not going to make you practice it. And we're kind of getting ready for tests, and I want you to kind of mellow out. Plus, the other thing I want to start showing you today is actually way more interesting to me and useful than this. So there's really only one more thing I've got to show you that you don't know. You down with that? Does that make sense? Why don't you take a stab at the second one, at least to get it started? Do you notice from your previous studies, as you begin this question anyway, do you notice that this statement right here, its derivative happens to be sitting out in front? That is very nice. If that had been x cubed out front, this problem would not be doable. But its derivative is sitting out front. So can you make a substitution to at least get started with this question? That's going to simplify it greatly. I'm just going to give you a second to kind of think about that. It's just a huge, ridiculous statement. It's like integration by parts because it's x to the 4th times tangent. And then it's not even just tangent, it's tangent cubed. Ugh. Who thinks of these things? Just to make sure you're getting off on the right foot, if you say, let's let u be equal to x to the 5th, and thus du would be equal to 5x to the 4th times dx. So, and I usually don't write this down, so that means dx would be replaceable with du over 5x to the 4th. Oh yeah, there's an x to the 4th out front. That's going to be sweet. I'm hoping you saw that before you even started. That's one of the keys that substitution is really a good idea. So you say, awesome, I can write this out then. I have x to the 4th, and I have the tangent cubed, but now I can say that's just of u. And I left x to the fourth there because I understand that dx is replaceable with du over 5x to the fourth. And so, bam, x to the fourth gone. Whew, that was a big dodge. That was huge. So that means, hey, all the x's are gone. And so this problem becomes, hey, there's a 1/5, but remember, I'm not intimidated by that. I can pull that out front, and now I have there. That's simpler. However, we're still not out of the woods, right? That's still legit. I don't know what the integral of tangent cubed is. I can't remember if we made it in class. I'm thinking to myself, was this one of those? And I'm thinking about the trig substitution chapter was like around 8.4, somewhere in there, 8.3. It's kind of like, well, let's see, should I tangent squared is equal to secant squared minus 1? Do I replace tangent, one of those tangent squareds to secant squared minus 1? And then do I make some other substitution? So, that's hard, right? I mean, we got to try stuff. There's no obvious answer to that. We did not practice enough that you should just immediately know what to do. I don't immediately know what to do. So I'm just, if I had to do this by hand, I'd be thinking, I guess I might try that. Maybe I'll switch tangent into sine over cosine. That'd be sine cubed over cosine cubed. I just have to play around with it. And there, because it's a book problem, then you'd assume there actually is a way to solve it. But in the real world, there might not be a way to solve it. We don't know. So we say, great. Well, in this chapter, I'm free to look in the table. Now, can you appreciate the black? The original integral is probably so complicated it wasn't in the table. However, I bet tangent is in the table. So are you looking at the table? I'm going to go there again. Is there an integral for tangent cubed? And so notice this was titled trig functions with e to the x in them. And so now I'm looking for something that's probably just titled trig functions with, that's got x's in it. Hey, we had a trig function with x in it, but I bet the one we were doing isn't in there. What about just regular trig functions? Oh yeah, regular trig functions. Now I'm looking for tangent. Bam, there it is. Number 72, the integral of tangent cubed. Woo, man, that's ugly. Look at that thing. Natural log of cosine plus 1/2 secant squared. Man, that is ugly. I wonder if I could make that for myself. I hope you think. So let's use that. We're free to use the table. Let's crop that dude down so we aren't distracted. Beautiful. Awesome. Hey, sweet. I'm done. I'm home free. This is easy. Except for I have u's instead of x's. So this, I'm done. So I have 1/5 times this new answer, the natural log of the cosine of x, but for me, x is u, plus 1/2 times the secant squared of x, but for me, x is u. Bam, I'm done, except for I just need to go back and replace u with what it was equal to with x, and then I'm completely done. You'd be welcome to distribute 1/5 in there, but who cares? Cosine of x to the 5th plus 1/2 secant squared of x to the 5th. Technically plus c. Bam, I'm done. So I still had to do a little substitution, but I got it to look like something in the table. So the idea is, if you get an integral that's really hard looking, and you can see that we could go down this road, and I see why a book would do it. And if we had, 5 more weeks or something, I think that might be worth thinking about for those of you that are, math majors and so forth. But it doesn't have to be in the table to use the table. That's kind of the thing I want you to see. So the other thing I'm a little curious about is because we live in an age that's, far beyond kind of what people typically do here. So let's just play for a second. Let's play with that question. E to the 4x sine of 4x. We got the answer to it. Let's remember Let's remember what it was real quick. Sine of x, okay. And I've shown you this already as well. But there's a couple of places you can go. Probably my favorite one that I've mentioned to you is CY Math. Let's see if CY Math will give us the answer to that problem we just were wondering about. In other words, this is even better than looking up things in a table. Where's CY Math? How come it's not there? There it is. So, a table's limited because, well, this table was maybe not big enough. Maybe there's huge tables that have 500 integrals that people have written them all down or whatever, but we have some pretty sophisticated software now. Remember, this one's free. I'm sure there's some software you could pay for that would definitely answer this. So let's see. I don't remember how to ask this. Do I say integrate? There we go. I started typing int, so it's integrate. I was going to say find the integral, but integrate. I want to integrate. What is it? E raised to the. Probably have to put that in parentheses. What's happening? Times the sine of 4x dx. Notice when I type dx, it doesn't need it. See how up above it's like in there twice, so it's letting me be lazy and not even put it in there. So apparently I have it typed in right. Again, that's kind of a cool thing about CY Math, is it's kind of saying this is what I think you just typed. Is that what you just typed? And I'm thinking, yeah, baby, it is. Enter, bam. Does it do it? I don't know. Bam, no problem, it says. Integration by parts. It even shows you how to do it longhand. And so, is that basically, whoa, look at that, 15 steps. Is that the answer we got? Yeah, they distributed the 1/8 inside. Notice we had a 1/8 and an e to the 4x outside, kind of factored out. And then there was a sine of 4x minus cosine of 4x, and they just distributed it in there for some reason. So cool. Wow, to do that by hand, 15 steps. I like the table. I like CY Math even better. My guess is it won't be able to do the one we did just a second ago because it seemed kind of complicated, but I don't know, let's give it a chance. It was x to the 4th. X to the 4th times tangent. Let's see, I'm not exactly sure how to type this. I'm going to put an extra set of parentheses. Tangent of x to the 5th. Close that parenthesis and say squared. Yeah, that's it. That's what I wanted.
Wasn't it cubed?
Cubed. Thank you, Eve. So that's not the way we usually write it, but with the extra parentheses, I got it right. Let's see if it'll do it. My guess is no. It says, yeah, no problem. So remember my guess? So it got it down with the same substitution we made to the 1/5 tangent cubed. And then sure enough, that suggestion that I had in my mind, like, do we replace one of the tangent squared? Do we replace it with secant squared minus u? So yeah, and then they went on to do it. And so, in the end, did they get the same answer we got? I hope so. Cosine x to the 5th. That's interesting. No, not really. It's in a different form. We had natural log of cosine x to the 5th. They have natural log of secant to the 5th, but notice it's a negative. So remember, with logarithms, the negative can go up in the exponent. So that'd be the secant to the -1 power, which makes it cosine. So despite the fact that doesn't look the same, it actually is. So we'd have to play with it to get this to look the same, because remember, trig is annoyingly constantly, you can rewrite it so many different ways. And so that's actually kind of cool. I mean, it's amazing. I'm surprised. I didn't think it would be able to get that one. I thought it was really weird.
Could they just move a 2 in front of the natural log and make the denominator 10? And that would just kind of, or am I screwing up my order operations there?
No, in other words, if you, that's
for the 5, yeah.
Yeah, if you put a 2 here, so you multiplied the top and this bottom of this fraction by 2, so now that's 2 and it's over 10, and now they're both over 10. Yeah, absolutely.
All right, cool.
So it doesn't immediately look like what we have. And you probably don't remember it because you probably weren't writing it down, but it's similar. Let's try sine of x divided by x. What do you think's the deal with that? Like, that seems pretty easy. So bummer. What does that mean? Does that mean you can't take that integral? Does it mean it's too hard for CY math? Notice we don't know. So does it make sense that apparently it's hard because it just got a couple of really hard ones right, and then suddenly this one that doesn't seem that hard didn't seem to be able to get it. I know in class we used integration by parts for that one. This is, I think, the first question I ever used to teach you integration by parts, and so it says by integration by parts, and then it answers the question. So it seems to have no problem with x times the sine of x, but x divided by, or sine of x divided by x, it seems to, that's not very easy. And so the thing I want you to understand, and I've hinted this to you guys a little bit because this is where we're going to go now, is there is a gazillion integrals that you can't take. There is no way to answer them. And so fortunately, there's some numerical ways where you can actually get an approximation to this. Now, you can't get the answer to this as an indefinite integral, an integral where there's no limits of integration. But if we say we want to know that area from 2 to 3, we can get it. Now, again, we don't need any techniques for that because we can cheat in Desmos, right? Just for the fun of it, let's see what Desmos says about this since I'm here. So Desmos is not smarter than CY math. Desmos is not taking integrals. So if I say, I just want to see what the graph of this looks like. F of x equals sine of x divided by x. So notice that's kind of a fun looking sine wave that seems to dampen to 0. Isn't that kind of cool? It kind of oscillates, but it sort of dampens to nothing, kind of like a spring bouncing back and forth and oscillating to nothing. But I needed to see the graph because I needed to see the area, make sure the graph existed if I went in and chose an integral for it. So let's see if Desmos will give us an answer from, I don't know, notice it seems to hit out there at 2 pi. So let's just say from 0 to 2 pi. Let's say what the integral of that is from 0 to 2 pi. So since I went to the trouble to call that f of x, then I don't have to type it again. So is Desmos going to answer this question? Notice it says, yeah, no problem. So because of the world that you live in, the last chapter that I want to show you could be, for many of the questions, could be looked at as not necessary. In other words, we have a way of cheating to get the answer to any definite integral we want. And so even though the actual integral of the sine of x over x might be impossible or at least really hard, and I find myself wanting to look at integral tables and kind of see, is there an answer to that question, or why is that so hard, and could I use integration by parts? If I think of it as 1 over x times the sine of x, could I use integration by parts? That's 2 things multiplied, and I kind of want to play around with it. But I'm getting the sense, and I tried that question before class, I'm getting the sense that's going to be hard. That's harder than it looks. It's amazing that e to the x sine of x actually had an answer, and that was pretty brilliant that somebody came up with a way to get out of that mess. So what I want to show you is kind of how to think about this. And so let's see. Let's do this. Let me show you a couple of the numerical strategies now. So let's stop sharing. And share back my other screen. As I've said, if you're kind of a true mathematician at heart, maybe the fact that I just threw up that problem, the integral of sine of x over x, it's like you're now done. Like you don't want to listen to class anymore because you want to go play with that and try to, see what progress you can make and see if you can substitute it into some other integral that you can actually take, or maybe use integration by parts. Notice it doesn't look like a trig substitution. There's no Pythagorean theorem in it. It's not sine cubed or something bigger. And so I kind of feel like those are my only two tools. And so I want to play around and see if I can come up with an answer to that. I mean, a true mathematician is bothered by that and really wants to kind of understand, because it's the first time I've kind of talked about the fact there's actually tons of integrals you can't take. And so numerical integration that I'm about to show you is a really powerful idea. But again, you non-mathematicians, that the skill I'm going to show you here is a little bit obsolete. Well, a little bit. There's some things I'm going to show you that are really cool. The last project I'm going to give you pertains to this. But there's ways you can actually get approximations that are ridiculously good. Don't forget, when we first started this class, and this is where we're going to go now, that all we ever did to find the area under a curve is just approximate it with rectangles, right? So in a sense, that's what we're going to do here. So I showed you a little bit about tables in 8.7, and now for a day or two or three between the project and 8.8 numerical integration. We're just going to spend a few days on this, and this is a powerful trick. Otherwise, I wouldn't be showing it to you. It isn't obsolete because of Desmos and your graphing calculator. So let's start with something that we're pretty familiar with and we already know the right answer to, just to kind of see how good of a job this does. But I'm going to show you some things. Well, to start with, I'm going to show you some things you already know. So let's say we wanted the integral of x squared, just to keep it super simple. And we know that's a parabola, and so let's take it from, I don't know, 1 to 4. Say we want to know that, and you would say, yeah, I know how to get that exactly right. I can get the perfect answer to that. And that is now an easy problem to me. That's a super easy integral. We love power rule integrals. And so, but we're going to try to approximate this. We're going to pretend this is like sine of x over x, where we can't find the integral. So let's just do it with something where we know the answer. Let's see, that'd be x cubed. Let's get the right answer to this really quick. The right answer would be x cubed over 3 evaluated at 4 and at 1. 4 cubed is 64. So that'd be 64 thirds minus 1/3, which is 63 thirds, which is 21. So the right answer to this is exactly 21. And we got lucky because it wasn't even a fraction. I think it's 21. Anybody see anything I did dumb there? 4 cubed over 3. I don't see anything dumb. I think it's 21. So let's approximate this. We know the right answer. Let's find an approximation for this. Again, because there are problems we can't solve. So let's make a graph of this. Let's make some graph paper so we can make a decent graph. Better use smaller pixels, because 4 squared is 16. So this is a rather large graph. So let's figure this out. So there's 2, 4, 6, 8, 10, 12, 12, 16. And that's what I'm at a distance of only 4 away. So we're talking about this. So x squared, when you put in x is 1, you get 1. When you put in x is 2, you get 4. When you put in x is 3, you get 9, 5, 6, 7, 8, 9. And when you put in x is 4, you get 16. And so this is the parabola that we're looking at, the right side of it. Try to not do too bad of a job sketching it. And so we want to know that area over there. So what we did early on when we were trying to just get the idea of this is we approximate it with rectangles. underneath it. But this is such a steep shape that that's going to be terrible. So we have a few techniques. And one of them you already know. So let's do that one first. One of them is the midpoint method. So let's talk about that. We're going to need this again. I'll probably move it to somewhere else, but right there. So midpoint is this. It's super simple. You already know this, I think. You say, let's break this into rectangles, but how many rectangles shall we make? Now, the easy answer to this would be 3 of them. Do you understand that? Because, well, since I'm going from x is 1 to x is 4, and the picture that I drew, I'd make that really easy just to use 3 rectangles.
Shouldn't we do as many as we can?
Yeah, and so the limitation is, let's do lots of rectangles. So if you don't have any concerns about time, then you can say, let's have 50 rectangles. The problem is then you actually have to add 50 things together. And so the idea in this section is there's some things we could do that would keep us from having 50 rectangles or 100 rectangles and still be able to get a pretty decent answer. That's kind of the idea in this section. Now, remember, because of technology, and I showed you how to do this in Excel, we could just have 500 rectangles and get a pretty decent answer. But let's decide to do something a little weird, because this is true in your assignment. Let's pick a number that isn't so nice, like 5 rectangles. So that's kind of terrible. So remember that to get the change of x, or the size of your rectangle, you're going to have to say, okay, well, how far am I going? I'm going from 1 to 4. I have a distance of 3 to work with. And somebody decided to divide it by 5 rectangles. And so my rectangles are 3/5 wide. And so that's kind of lame. So now I've got to divide this thing into 3/5. So that's kind of stupid. And now I'm sort of regretting having such a steep shape, because it's going to be kind of hard to draw this. But I guess we're this far in, so let's keep going. Let's see. So I'm going to try to approximate 3/5 here. So between 1 there, 3/5 would be about right there. And let's see, another equal amount, that'd be another 3/5, and another 3/5 would put us about right. 1, 2, 3, 4, that's 5. 3/5. 3/5 is a little over. Is not that much past a half. I think I'm going too far. 3/5 is more like just a little past half. So it's probably about there and there. There we go. 5 rectangles. So the key is that you understand that the width of that rectangle is 3/5. That's what you need to understand. And so then I say, okay, great. Well, let's fill this thing up with, well, what are we going to fill it up with? In this section, we're going to get a little more creative about what we actually fill this thing up with. And we got this one on the end. Goes all the way to the top. So do you understand from earlier, the question was, how tall shall we make these rectangles? We had a left ream on some where we said, oh, let's make them that tall. That's how tall they'll be, which means our estimate will be an underestimate early on. But if we're going to stop, kind of screwing around, like, let's make an estimate that makes more sense. Well, you can probably appreciate that since I said this is called the midpoint method, that's what we're going to do. Instead of picking the left or the right, since this is so steep, we're going to pick the middle of it, the midpoint. In other words, I guess you could say this point. That's how tall it's going to be for us. We're going to go there and figure out how tall it is. This is where we're going to get our heights. So that's how tall this rectangle is going to be. That hits about here. This is how tall that rectangle is going to be, and so forth. Does it make sense if you don't want to do a lot of rectangles? Can you visually see this is a pretty good idea? In other words, this rectangle is going to give us too much area there, but it's going to miss some there. The balance of that is this is going to be a pretty decent estimate, and I only have to do 5 rectangles. See the logic in that? So this one looks like it lands about there. So this rectangle is that tall. This last one lands in here somewhere. So it's going to be that tall. So we're going to find the area of those 5 rectangles added together. Now the problem is we've got to find the height of those. How tall are those rectangles? We got to figure out where the heck that is. In other words, what are these locations right here? Well, would you agree that one is, well, we started at 1. And if we're going to go halfway, instead of getting all the way, this is so painful with weird numbers, but your assignment does it this way. If we're going to go from here all the way to here, this would be 1 3/5. That's what I'd be plugging in to get that height. But we'd need half of 3/5, which is actually 3/10. So that location right there is going to be 1 3/10. That's what I'm going to have to plug into my equation. So I need f. I need the function evaluated at 1 3/10. Fortunately, we got lucky. That's at least a decimal enough to type 1 3/10 in. That'll be the height of my first rectangle. What about this next one? What's its height going to be? Well, would you agree that if I jump from here to here, that's 3/5 again? So it's really 1 3/10 plus 3/5, which is 6/10. I guess that's 1 9/10. Or 1.9. So these are my heights. I'm going to have to plug in 1.9. Like, notice how much of a pain this is. I'm going to show you on your calculator how to make this, how to kind of make quick work of this. But I'm finding the heights based on midpoints. So given that 3/5 is 0.6, can I speed this process up a little bit and say, well, if I add 0.6 to 1.9, wouldn't that be 2.5? And if I add 0.6 to that, isn't that 3.1? And if I add 0.6 to that, isn't that 3.7? Something is wrong. No, it's not. We're good. And so there's my 5 rectangles. So just to check, half of 3/5 is 0.3. Does it make sense if I added 0.3 to this, I'd get to 4? That's my endpoint. So there's my 5 rectangles. I didn't screw up. So I got to get all those heights. Now, in our case, I'm not going to cheat on the calculator just yet. All I have to do is plug those into x squared. So if I say 1.3 squared, I can get these without really working that hard. So that's height is 1.69. 1.9 squared is 3.61, and so forth. Do you know how to get this, your calculator, to spit all of these out for you? I just thought it wasn't worth our time for me to switch screens right now.
Didn't we build a program that ran the left Riemann sum like in the second week of class?
That's exactly right. And so could you modify that program, use technology, if you will? Could you modify that program to do the midpoint instead? And then you could have, you don't have to have 5 rectangles. You could have 50 rectangles and then get a ridiculously accurate answer. So you're exactly right. If you invoke technology and you see the repetitive nature of this, then yeah, absolutely. So do you agree that every one of those rectangles has the same width, which is 3/5? And so all I have to do then is take my change of x, let's write that up here, my change of x, and multiply it by each of those values, by f of the sort of first midpoint plus f of the second midpoint, and so on and so forth. Like, that's all we're really going to do. It's just left and right Riemann sums. We're just choosing the middle, and you can see that most things are curved, and so this is going to be great. So if I take my change of x, which for us was 3/5, and I multiply it by all those numbers added together, I got a pretty decent approximation. there's a part of you that should be saying, this is kind of a waste of time, but I'm going somewhere with this. There's a couple of better techniques that we haven't looked at, and one of them is breathtaking, called Simpson's rule. So in a practical sense, you would never use this one because it's not very good. And we can get a way better approximation using a couple of different techniques. So I'll show you that in a second. We're getting there. So I'm quickly typing this in so as not to waste too much time. And I got 20.91 for the sum of all those times 0.6. I got 20.91 for the area. What's your thoughts on that? Dang, that's pretty good. We only had 5 rectangles thanks to choosing the midpoint instead of a left or a right Riemann sum. We got that within 1/10 of the right answer with only 5 rectangles. That's actually pretty impressive. Let me show you an even better way. Let's not find the area of rectangles like we always did. Let's not find the area of rectangles defined by midpoints. Let's find the area of trapezoids. How would that work? First of all, can you see just by me throwing the word trapezoid out there where this is going? Like, what are we going to do then?
Well, the edges that stick out and go inside of the function are going to be closer.
Yeah. What we're going to do this time is say, okay, well, let's not find the area of rectangles. Let's find the area of trapezoids, and let's build this formula, because again, I'm interested in you learning to think. These are just cool ideas. I can just show you the formula that's in the book and we could get on with it. That was a mistake. And we could get on with this, but let's just figure out how people built this stuff. It's kind of cool. I certainly did not copy this at the right time. But this doesn't have to be perfect. We'll get close. So would you agree that those 5 divisions we decided to make, if I came back here and said, well, why don't we just find the area of that trapezoid right there? Notice how straight the parabola is. It's pretty close to straight out there. So I wonder what kind of approximation I would get if I just used straight lines connecting these. I thought of those green shapes as trapezoids. Notice the cool thing about this method, number 1, it's actually going to be better. And number 2, I don't have to work so hard to find the stupid midpoints. In other words, this is at 1. So that's f of 1. This was at 3/5 more. So that's f of 1.6. In other words, I can actually just use the points that I found. So notice my change of x has not changed. I'm still stuck with 3/5 or 0.6 for my change of x. So every one of these points right here, I just need all of them. Maybe I'll write it like this. So this is the 0.1, that's the 0.1.6, that's the 0.1.9. This is 2.5, this is 3.1. No, I'm screwing up. That's not true. What is wrong with this? I just got the second one wrong. I got excited. I'm adding 0.6 every time. So this is 2.2, this is 2.8, this is 3.4. Notice that end one, if I add 0.6, is actually 4. In other words, I don't have to work so hard to find the midpoints. Where fractions are involved, that's kind of a pain. But you remember this. What do you do to find the area of a trapezoid? If this is your width down here, change of x. What do you have to do to find the area of a trapezoid? You're really
Wouldn't you,
just good.
wouldn't you make that pointed part into a triangle, solve for the area of that, and then add it to the area of the rectangle?
Yes, you can break that shape into a triangle and a rectangle, but kind of the faster way, the easier way, is to say, you know, if this is like height 1 and this is height 2, what you're really doing is taking the average of those. So I'm going to take the area of that shape, then will be the change of x, which is kind of the height of our trapezoid. Notice this trapezoid is turned sideways, times the average. That's the kind of the classic formula for area of a trapezoid that is found by breaking, to your point, Jaleesa, breaking the trapezoid into a triangle and a rectangle. That's where that formula comes from. So you're just taking the average of those two heights. Does it make sense? The average of those two heights is not the same as the midpoint. That isn't necessarily going to put you in the middle. It's going to be near it, but it's not going to put you exactly in the middle. So this is kind of a cool formula. Watch what happens if I kind of do this. So if I say, okay, then that for us, that means I'd be taking the change of x. I'll just go ahead and write it out. I'd be taking the change of x, which for us is 0.6. And that's what every one of them will be multiplied by. So that's kind of outside. And so inside, I'm just going to have the average of the two endpoints. So if I take 1/2 times the average of 1 and 1.6, does that make sense? That takes care of the first one. There, I got my first one now. So I'll take 0.6 times that, and I'll have the area of that first trapezoid. And then I'll take the average of the next trapezoid, which would be, well, notice 1.6 gets reused again. And now I'd be up to 2.2. And so on and so forth. I'll write a couple more because I want you to see the formula for this. Plus 1/2 times, so that takes care of this one. And then the next one would be 2.2 gets repeated again, plus 2.8. Maybe so that you can see this, I'll write them all really quick. And then from 2.8 up to 3.4. And then finally from 3.4 up to 4. If you were to speed that up though, what do you notice about that? I don't want to type that whole thing in, but what do you notice about this and this and that and this? What's a faster way to do this?
Just add 0.4 to each one each time.
Well, notice there's,
Well, no, they're more than 0.4, sorry.
Well,
You
couldn't
just represent
distribute
them
out
as like x0, x1.
say that again, Eldon.
Wouldn't you just represent them as like x0, x1, x2, and so on? Yeah,
that's exactly right. And notice in the end, we have 1/2 times the first one, x0, or first point, which is 1. But then we have 1/2 of 1.6 and another 1/2 of 1.6, which means we don't even have to cut 1.6 in half. And we have 2.2, 1/2 of 2.2 and 1/2 of 2.2, which is all of 2.2. And the same thing with 2.8 and the same thing with 3.4. But notice the 4, the one at the start and the one at the end are halves. Does that make sense? So I'm not going to write out the formula. The formula is sitting in your book. It's on page, I don't know, 500 and something. 571, where it writes it formally. But does it make sense? All you have to do is kind of get all your numbers, get all your values, and then Well, plug them in. Notice it's not just 1 though. It's f of 1. Does that make sense? In other words, I got to get the height. I can't, it's not 1. 1's not the height. It's the height. It's not 1.6. It's f of 1.6 and f of 2.2 and so forth. So because there's only 5 rectangles, let's quickly plug that in. So I have 1/2 times f of 1. 1 squared is 1. So that one's easy. 1.6. Something going on there. Is that you, Justin?
Sorry.
So f of 2.2, the height is 4.84. F of 2.8, 2.8 squared is 7.84. Again, I'm doing this slow because I want you to understand conceptually how this works. This is not hard. 11.56. That's 3.4 squared. And finally 4. When I put 4 in, I get 16, and 4 squared is 16, but I have to take half of that 16, and now I'm at the end. And so if I add all of that junk up, 1 plus 2.56 plus 4.84 plus 7.84 plus 11.56 plus 8. Since half of 16 is 8. I get 35.3, so 0.6 times 35.3. And when I multiply that times 0.6, I not surprisingly get something really close to 21. But notice this time it was actually an overestimate. Our last problem, we got 20.9, and this one's like 21.2. So we're 0.2 off. Overestimate. Notice in this problem, because we have the right answer, we know how far it's off. But if we were doing this with x sine of x, we wouldn't know, or something of that nature, we wouldn't actually know. Now, all of this, my friends, pales in comparison to the glorious Simpson's rule. So watch this baby in action. I'm going to write Simpson's rule down formally for you, and we'll decide later whether I'm going to show you where it comes from or not. Some of you might care and some of you might not. Simpson's rule says, if you take the change of x and divide by 3, and multiply it by the first height, so f of x0, let's see, am I going to say f? I guess I said f before, I'll do it again. So the first value, whatever first value is, so for us a second, it's the height of it, it's not the 1, it's f of 1. And then you add to that 4 times f of the next value. And by the way, this is the same exact values we had right here. 1, 1.6, 2.2, 2.8, 3.4, 4. Just those 5 values. Notice it takes 6 values to make 5 rectangles. Does that make sense? 6 values to make 5 rectangles. Oh crap, this isn't going to work because I made 5 rectangles. Plus 2 times the next one plus 4 times the next one plus 2 times the next one, and then you just continue like that, 4, 2, 4, 2, 4, 2, 4, but then it finishes by 4 times the one way the heck out there, and then finally just 1 of the last one. There's Simpson's rule. So Simpson's rule has to work like this. It starts with 1 and it goes 4, 2, 4, 1. Like that's a possibility. It's got to end with 4, 1, where you could be 1, 4, 2, 4, 2, 4, 1. It's got to have that pattern to it. It's got to be symmetrical. It can't end with 2, 1. Does that make sense? You can't go 1, 4, 2, and then 1. It's got to end symmetrical. Now, what does that mean? I want you to think about this for a second. It's the only thing that's a little strange about Simpson's rule. So how many values did I have right here? 1, 2, 3, 4, 5. How many rectangles is that?
5?
No, 5 endpoints.
Oh, 6.
But that's going to put between them, there is a rectangle, there's a rectangle, there's a rectangle, there's a rectangle. That's n is 4. So in our last problem up here, we had, count them up, 1, 2, 3, 4, 5, 6 numbers that we used. And those 6 numbers created 5, n is 5, right? N was 5 for us. That created 5 either rectangles or 5 trapezoids. And so the limitation to Simpson's rule, you can't have 5 rectangles. Notice in this next one, 1, 2, 3, 4, 5, 6, 7 endpoints. That's n is 6. You actually have to have an even number of rectangles.
Is that kind of like Pascal's triangle right there?
It's kind of related to that, but I mean, it looks like
Not.
that. But because it continues with only 4s and 2s,
Oh, it's only 4. Okay, never mind.
there's no other numbers. It just goes 1, 4,
Yeah,
2,
yeah.
4, 2, 4, 2, 4, 2, 4, 2, however many you want. And so let's do something. Let's actually make it worse. Let's use Simpson's rule, but let's make it worse and just use 4 rectangles. And again, I'm not telling you what this is actually doing. This isn't using rectangles at all, or trapezoids, or any shape you've ever even thought of. Let's use n as 4. So let's think, we got to kind of do the math on this. So let's see, we went from 1 to 4. So our change of x is 4 minus 1, but divided by 4. So this time our gap is 3/4. So that means we started at 1. So our first one is 1. We know 1 squared is 1. And then we got to go 3/4 above that. So that's 0.75. I'll just use decimals so it's obvious what I'm doing. And if I take 1.75 and square it, I get 3.0625. And then I go another 0.75, which takes me up to 2.5. When I square that, I get 6.25. I think 25 squared is 625. And then when I go another 0.75 above that, I get 3.25. When I square that, since my formula is so simple, I get 10.5625. And finally, I get up to the end point, which was 4. 4 squared is 16. So there's my 5 numbers. It takes 5 numbers to make 4 rectangles. So what does Simpson's rule say to do? It says take your change of x, which is 0.75, divide it by 3 from nowhere. Where did 3 come from? And then just add those numbers up, multiplied by 4s and 2s. So the first one's multiplied by nothing. The second one is multiplied by 4. The next one is multiplied by 2. The next one is multiplied by 4. And notice the pattern worked because it went 4 and then the last one is multiplied by just 1. If I add all those up and multiply, you do this really quick. Add all those up, multiply by 0.75 divided by 3. What do you get? Notice how easy on a test it would be to just type one number wrong or something stupid. So it's like you got to kind of stare at this. What did you get? With only 4 rectangles. You're all saying
I
didn't.
got 21 exactly.
You get 21, which is exactly the right answer. With only 4 rectangles, right? Like I made it, I should have been worse because that was only 4, and yet we got actually the best answer yet.
I feel like you're lying to us. I feel like this is some
Yeah.
like who would think of 1, 4, 2, 4? I don't know. This bothers me.
Yeah. And that's my question is like, do you want to know where this comes from? Do you want to know, because it's a bit of algebra and so forth. And that's kind of why I decided to cancel the other section. I would like to show it to you. And we probably won't have time to show it to you today, but let me show you the theory about why it works. This is the brilliance of what this idea is. And so let's say the graph is here and some person decides they want to find, notice I didn't even name this curve. I just said it's a curve. So we're going to find its area from there to there, but we've got to use an even number of rectangles. So let's see, I could say, do I dare try 6 rectangles? This feels dangerous. 6 rectangles. So I divide it into thirds. Yeah, I can do 6 rectangles. So notice again, that took 1, 2, 3, 4, 5, 6, 7 points to do it. An odd number of points. So this one would be multiplied by 1, by 4, by 2, by 4, by 2, by 4, by 1. See how it's symmetrical? Like it works. It works because you chose an even number of rectangles. Did I say that up here somewhere? N is even. N is not even. This does not work. Now, here's what Simpson did. Extra credit. Was Simpson the inventor of this? Mr. or Mrs. Simpson, the inventor. And so that's why it got its name. What year was this figured out? What's the history of this? Was it named after Simpson who died? Was it Simpson who created it? What year? What can you learn about this historically? Here's what Simpson's rule does that is just genius. Simpson's rule says, well, the top of that shape is not straight. It is not a rectangle. That's terrible. And it's not even a trapezoid. Look how bad the trapezoid is right there. See how much area is lost right there because you made a trapezoid out of it, as good as the trapezoid is. What does Simpson's rule do? Brilliant. Simpson's rule finds, my friends, a parabola. It finds a parabola and then finds the area under the parabola. It makes a parabola out of every single curve. So every one of these is like a little parabola. Since most interesting shapes are curved, it's kind of stupid to make it straight. Now you might think, how in the world would you find the area under a parabola? And my thought would be, well, you have to do integrals. And remember, we're not supposed to know that. Like we don't know how to take integrals, or we can't take integrals. But remember, you can take the integral of a parabola. I mean, that shape a second ago, sine of x over x, it's some curve, but couldn't you approximate it with a parabola? And these shapes are curved. And so you're literally saying parabolas. That's what we're going to use. That's why the parabola just now came out perfect. Parabolas are the only ones that'll come out perfect. Parabolas will come out perfect every time because parabolas are parabolas. But any other shape, it's not going to come out perfect. And so that's why you thought I was lying to you, Eve, because that shouldn't have come out exactly 21. This is the genius of this. So effectively, the concept is this in Simpson's rule. If you take, and I just want to do, I'll do one more example and then we'll just pick it up tomorrow. But Simpson's rule says, okay, if we went to the middle of this right here, the midpoint actually, and we took these 3 points, does it make sense to you that you can find an equation for a parabola if you know 3 points? So I'm going to pick the end points and the midpoint. I'm going to find the equation of that parabola. And then I'm going to use integrals to find the area under that parabola. Even though the shape is a sine wave or something, I'm going to make a parabola out of it. Remember, this is just an approximation. It doesn't work exactly. So Simpson's rule results from the algebra of making a parabola out of that curve and then using calculus to find the area of it. And isn't it ridiculously simple and ingenious and miraculous? I love that you were bothered by that, Eve. If you were not bothered, then you're not paying attention. It's like, what do you mean? You 4s and 2s, and somehow that produces the answer to this. So I'd love to show you that tomorrow, because we'll run out of time if you'd like to know. But let's just do another example. Let's just see.
We should do the sine over x example. I want to know if it works
Exactly.
because it's a curved one instead of a parabola.
That's exactly right. Did we do that a minute ago? Like, what, didn't we cheat? Did we go from 0 to 2 pi? Yeah, we did. 0 to 2 pi. I'm writing it down. I just pulled it back up on my other screen. From 2 pi to 0 for the sine of x over x dx. Desmos told us the answer was 1.41815. Writing them all down. 15157 And what I don't know, my friends, is how does Desmos do that? It very well could be that Simpson's rule is programmed into it, because Simpson's rule is the best one. So Desmos told us that answer. Now let's see if we can actually get this figured out for ourselves. Now, let's see. Let's have, we got time. Let's do 8 rectangles. N equals 8. That's enough to be accurate, but not so many that I'm going to go insane. So let's do 8 rectangles. Now, let's do this a little more sophisticated this time, because I got to plug numbers in, right? Remember, n equals 8 means I'm going to actually have 9 sort of f of x's, right? I'm going to have 9 of those. So they start at 0. And what do we do? How do we get, like, what values are we actually figuring out here? It's f of, well, we started at 0 here. So f of 0, there's our first one. What's our next one? How do we figure this out?
2 pi divided by 8.
Yeah, 2 pi minus 0 divided by 8. So that's pi over 4. So there's our change of x, right? Change of x is pi over 4. So we just have to go pi over 4, and then another pi over 4, which would be 2 pi's over 4, which is just pi over 2, but I think I'll write it as 2 pi over 4. And then 3 pi over 4, and so on and so forth. And eventually we'll get up to 2 pi, right? 8 pi over 4. So this is a place where your graphing calculator really shines. One of the few places where your graphing calculator shines. Do you know how to use the table in your graphing calculator? So I went really slow and showed you these ideas, just super basic, drawing pictures, wrote every number out. It's like, this is such a simple concept, but let's speed the process up a little bit here. So go into y equals, let's see, I got to check, see what mode I'm in. I'm in radian mode. Awesome. And I want the sine of x, close that parenthesis, divided by x. And we already looked at the graph of this, but let's just look at it again really fast. So it looked like that from 0 to 2 pi. I guess I won't go to any more trouble, but let's go to table set right above window. Have y'all done this? Second table set. This is really cool. You say, where do you want to start? I want to start at 0. And how would you like to change? What would you like to go up? Well, I'd like to go up by enter. How do I get down there? Enter. I'd like to go up by pi, blunk, blunk, divided by 4. So you're telling it start at 0 and then go up by pi over 4. Notice it says auto, which means don't ask me, just tell me all the answers. And so if I now go not table set, but above graph to table, second table, there's my answers. Uh-oh, error. Maybe we better not start at 0. Let's see, sine of 0 over 0. Yeah, because it's 0 over 0, so it doesn't like that. What did the graph show us? So again, that's kind of why it's important to graph things. Let's see, I'm bothered by this way. It's 1. So you're all seeing that, right? Let's take a look at this real quick. Notice it's actually 1. The sine of 0 over 0 is actually 1. Isn't that weird? Thanks to calculus, we can actually answer that question because, and this is probably why you can't take the integral, I'm suddenly realizing. So technically there's a hole in this graph, right? So I'm kind of glad this happened because I'm always avoiding these little technicalities just so you understand the concept. But there's actually a hole right there. But would you agree the limit of it? So we can't say the sine of 0 over 0 is 1, but we can say the limit of the sine of x over x as x goes to 0 is 1. So would you agree it's 1? Even though the calculator says error correctly, says error. So there's your values, 1, 2, 3, 4, 5, 6, 7. Notice I can't see them all. There's 2 more. So I have to take these and multiply them by 4s and 1s and so forth. So I'm gonna write that onto my screen and then I'll switch screens. You do this ahead of me because you understand this now. And I'm going to carry those decimals. Those decimals are going out 5 places on here. I'm going to carry them out all the way because this is such an accurate technique that all those decimals actually matter. So my third one is 0.63662. Notice we got some negatives in there. So that's my 7th one. There's my 8th one. There's my 9th one. So the 9th one is back to 0 again. Yeah, the graph hit 0 there. That makes sense. So plus 4 times negative 0.1286. I'm just quickly typing this in my calculator. Again, just even getting the whole thing typed in your calculator without hitting the button wrong is no small deal. So there, I wrote it all out. Incidentally, I just got it wrong myself because I checked it against the answer. And the only reason mine was wrong is this parenthesis right there, that parenthesis, I hit it, but I don't think it showed up, and I got the answer wrong as a result of that. Like I have it all typed right here, but I missed it. And the only reason I knew I missed it is because my answer was pretty far from 1.418. So if you don't choke that, you end up with, well, pi divided by 4 divided by 3 is pi divided by 12. If you don't choke that, you end up with 5.42672. In a room this size, there's at least 2 of you. I guess one of them was me. One more of us that is going to have typed that in wrong. And when you multiply that by pi over 12, you get 1.4207. That is off by 2 thousandths from the correct answer of 1.418. 2 thousandths. Is that right? Did I say that right? Yeah. That's incredibly accurate. And that was only 8 rectangles. Like if you wanted to, you know, spend a little more time, then take it up to 12 rectangles or 16 rectangles or something. And this is what the project is going to be, get Excel involved. So, you know, it can do all this nonsense adding and all this stuff kind of automatically for you. Write a little routine in your calculator. That's why I showed it to you. If you wanted to have a cool estimator in your calculator, it'd be Simpson's rule, not left-hand Riemann sums. Simpson's rule is really cool. Notice it's the same exact values. Go ahead. What'd you say?
I got an answer that's a lot closer. I got 1.4178.
So what you're saying is maybe I made 2 mistakes all by myself. Did anybody else get a better answer than that? I'm going to go back and re-look it. Mine was close enough that I thought it must be right, but maybe I typed something in wrong. I hope you're right, because that's even better. Yeah, I did something else wrong. I'm done. So I made all the mistakes for the whole class. For some reason, I have a 5 sitting right there. I have 1, 2, 5, 8, 6. Should have checked my work. I'm going to go back and see if that's the only 2 mistakes I made. Maybe I made 3. It's very embarrassing. Yeah, so on the test, does it make sense it's important to show your work? Because I just got 5.41576 for that. And when I take that times pi divided by 12, sure enough, you were right. Thanks for saying something, April. 41784. Wow. That is unbelievable. Actually, I want to subtract that and see if I take that answer minus 1.41815, I get an error. Your assignment's going to ask you about this. Since I could cheat for this, I got an error of 0.0003. 10 or 3/10,000ths is all we're off here. And we did it with 8 rectangles. I mean, isn't that amazing? Remember, none of the people before you had calculators, even graphing calculators to get these answers. And so the ability to get a ridiculously good approximation like this with only 8 rectangles, that is unbelievable. Did you get the same thing, April? In case I made yet another error.
Yeah.
Cool.
Hey, Doug, I'm kind of confused. Like, why isn't this the gold standard? Like, if we know about this, why can't Desmos and all these other computers like do it?
I'd say it is. It would not surprise me if this was sitting in Desmos, like if somebody programmed it in there. This is the gold standard.
So all the integrals we've kind of been studying is kind of just like it's been using this and we haven't been knowing, or
Well, the cheat button, yeah. I mean, I think I'm not sure what's in your calculator. Remember, computers don't have limitations. Like a computer could do this with 900 rectangles, and even we saw this, right? Even if you do the left-hand Riemann sum and make rectangles, which is totally crappy, if you have 900 of them, it's still going to come out with a good answer. But like this is no more work. Does that make sense than what we just did a minute ago? It's no more work. You just got to multiply by a couple of 4s and 2s and divide change of x by 3. It's like no more work, and you get an answer that's 10 times more accurate. And so yeah, it actually wouldn't surprise me if that is what's programmed into Desmos in your graphing calculator. This is the gold standard. You couldn't say that any better than you just did. If you ever want an approximation, this is what you would do.
Okay, just making sure.
So I'll leave you with this. Now you still might say, if you're a practical person, this is all great, but remember, we just got it with Desmos. Like, you still don't really need to know this in the world. Does that make sense? But here's an exception. We'll talk about this, and this is kind of what your project is going to be about. Let's say I have a yard, which I do, that looks something like this, and you wanted to know the area of that. Now, in the case of my yard that I'm looking out the window at right now, there were no equations involved. I just painted it on the ground, kind of the shape I wanted. I think my wife did that actually. Based on some landscaping and stuff like that. But it's like, that's not a circle, that's not a parabola, it's not an ellipse, it's just some random curve. Like, it looked cool. So you're not going to find an equation for this. Does that make sense? Simpson's rule allows you to come in here and take measurements every so often, like this. Remember those y values we just got a minute ago? Like, who says those y values have to come from an equation? Couldn't you just measure this distance and measure this distance and measure this distance and measure this distance? Isn't that distance right there your change of x, like however far apart you decide to go? And as long as you make sure you have an even number of rectangles, let's see if I got lucky. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 rectangles, I got lucky. I just divided that into 10 rectangles. And so my first measurement is 0. My second measurement is however long that is. If I stick all of those in Simpson's rule right there, I'm going to get a ridiculously good answer for the area of that shape that is undefinable. Like, you can't do that with calculus. Does that make sense? Now, amazingly, you actually have to have calculus to invent Simpson's rule. It involves calculus because you can take the area under a parabola. Like, area under a parabola is area under x squared is x cubed over 3. So the Simpson's rule was made with calculus. That's why it's so powerful. But this, to me, is where it really gets powerful. Like, if you go online and say, what's the surface area of Crater Lake? How would anybody know that? Like, how could there be a right answer for that online? Because Crater Lake is, well, like this yard. It's just some random curving shoreline. And yet, those are interesting questions. People want to know, what's the area of the United States? What's the area of Oregon? Or what's the area of that volcano? Those kinds of things. And so you can't do this question without Simpson's rule. Does that make sense? A computer can't help you here. Like, Simpson's rule is the only way to do it. And so it allows you to find areas of weird shapes, even volumes of weird shapes that have no equation. Again, I've always thought calculus is really cool, but it's an oversimplification of the real world because many, many things can't be defined by equations. Now, you could make an equation for this, like a chunk of this right here, and say, oh, that's a circle, and then this is a parabola, and then that much is a circle, and this much is a circle. Like, you could do regression and make rough equations for that, and then just cheat on Desmos to find the area for sure. Absolutely. But Simpson's rule is actually way easier. So we'll look at some examples of that tomorrow. And you decide between now and tomorrow, do you want me to show you where Simpson's rule comes from? It's kind of cool. But I always go long, but I can't go any longer than 9:30. So stay after if you are bothered by anything that we have done.
I just had a quick question.
Yeah.
Are you going to post the project online so we can print it out today?
Yeah. And we'll either do that project. I'd say there's a better chance we'll get into that project on Thursday, but I think I will post it today because it's kind of related to what I just did right there. It's trying to take some measurements.
Okay.
No, that's not true. I forgot. We're doing something totally different. I have 2 projects for this, and that's not the one we're gonna do. Yeah, so I'll post it, but you're gonna need to do it in class together. So
Okay, yeah, I just have to print them out before class because I have 2
yeah,
classes.
I'll post it. I'll post it today.
Thank you.
Yeah.
Yeah, I'm gonna say this chapter has been the hardest math I've ever done.
You're not wrong. Yeah, integrals are deep water, man.